Next, I'd like to welcome Professor Jessy Grizzle, who received his PhD in electrical engineering from the University of Texas at Austin in 1983. His research interests have often focused on theoretical aspects of nonlinear systems and control, including geometric methods for continuous and discrete time systems and observer design in discrete time. He has been a consultant in the automotive industry since 1986, where he jointly holds 16 patents. He is a full professor at the University of Michigan in the Control System Laboratory of the Electrical Engineering and Computer Science Department within the College of Engineering. He is also director of Michigan Robotics. Please join me in welcoming Jessy Grizzle.
Thank you, Phil. Thank you very much. Very, very happy to be here today. So the first message I want to share with you is that robotics is really a team sport here. You don't get anything done on your own. And I really want to send out a sincere thanks to our founding director. I'm often introduced as the inaugural director. It is so not true. Dawn Tilbury is the one who got everything going. She's the one who had the skills to build consensus and get the entire faculty together around a common theme, and my job now is to execute her plan without messing it up too much. So Dawn, wish me luck. Ella Atkins is running our graduate program. I'll give you some details on that. Chad Jenkins and Jason Corso have been doing a tremendous amount of work on our executive committee. Sarah Sobak, we just hired her this year to get the graduate program going and providing adequate services to our students. I want to really thank Sarah. Peter Gaskell has been responsible for building up all of the hardware for the labs, and he will now be a lecturer, we hope, coming soon. And then our newest staff member, a very important person, Damon Provost, who is the managing director. So if anybody here from industry has any interest in us, please contact Damon. So this is what robotics at Michigan looks like now. I mean, not all of these people are doing robotics full time, but these are all people who want to be associated with our activities. And I think what really makes us special, though, is this. You know, often people think of robotics as AI, etc. So at Michigan, it is so much more than that. We are very much heavily invested in hardware. Our motto, as I will call up in a second, is that we are algorithms in motion. So if you want to think about what's going on at Michigan, it is smart people dreaming up mathematical algorithms, programming them up in various software environments, and testing them on hardware. We have people from aerospace, biomedical, civil, computer science, electrical, industrial, mechanical, and naval architecture and marine engineering. I mean, there's hardly any other robotics institute that has that kind of breadth. When you see robots that are walking around really slowly, or it's taking a minute and a half to get an object off a shelf, that is not us, okay? We are so much not that. Our second motto is robots that move at the speed of life, okay? The same speed you do. And then we have this broad spectrum of coverage. So this is a video that covers some of the activities, whether it's on land or underwater or in the air, or building hardware to be super efficient, algorithms to make machines autonomous and work around people. Yes, we do work with M-City. We have great activities for students learning. Impossible robots doing absolutely wondrous things. And we'll talk about our work in rehab robotics as well. Now, the only thing we're missing is a couple of students like this last guy from the Discovery Channel, who is just completely covered from head to toe in tattoos. So if you want to have total diversity at Michigan, we need a few more wild people to show up, okay? We've got a really nice building coming online. It will be up in about 2.5 years. Ford Motor Company has leased the entire 4th floor. They will have a large number of engineers on site working with us in robotics, definitely, working more broadly in the automotive sector, but also in material science. About 130,000 square feet of space, and there's plenty of state-of-the-art labs, classrooms, etc. So let me just give you an idea about this building. I would like to be able to show you pictures, but they are all embargoed until they get through the region. So next year. So we'll have offices for about roughly 30 faculty. I think there's about 15 of us ready to move in now, so we still got quite a bit of hiring to do and a large number of graduate students. It's going to be a beautiful space for undergraduate student teams, and they'll have state-of-the-art shop facilities to work in. Of course, what would Michigan Robotics be without some tie to the automotive sector? We need more classrooms on North Campus. We'll have lots and lots of places where you cannot go from an office and exit the building without going through what I'm calling our Italian piazza. If you want to go to a lab, you want to go to an office, you'll have to go through our collaboration space, and this is where the ideas will happen. Just a random, unplanned encounters. We are insisting on food. All the engineers are going to North Campus are going, yeah, we don't want to walk over to Commons for everything. And then there's going to be gorgeous, gorgeous lab space. And for all of you teachers here, the labs are designed to have glass walls. So this building is tourable. We want you all to come by, and it will take almost no planning for us to say, yes, come on over. So teachers, definitely keep us in mind. We launched our master's and PhD program in 2014. The program was actually approved in January. Recruiting of students normally takes place in January and February, so we had to steal a few students from existing departments. So we started out very small with just 5 PhD students and three master's students, but this year we'll bring in at least 15 more PhD students and holding steady around 30 to 35 master's students. The applications are growing. Our first year, well, last year, 2015, it was more like 100. Last year in 2016, 300. This year, over 600. And of that 600, 300 were applying for the PhD. The education program trains our students in all of the key areas of robotics, whether it's sensing, reasoning, or acting. The MS degree and PhD degrees are Rackham approved, okay? I will tell you a little bit more about the 2 key courses, but when our students come out of this program, they're super highly sought after. Students this year, in between their first and second year, are getting internships that pay the same salary as an assistant professor at the University of Michigan. Now that's either way, way wild for the interns. They're like $8,000 a month, ladies. That's a good salary, okay? It's almost $100,000 a year, okay? You want to be a roboticist. And young assistant professors are getting about that much a year, too. So more salaries for the professors, and we'll keep the internships high for the young ladies. So this is the robotics boot camp. So the students come in their first semester, they're taking a math course I'll tell you about, and a hardware-centric course. In the hardware course, they're getting lots of skills in sensors, whether it's encoders, gyros, cameras, doing real-time path planning of robot manipulators in the face of obstacles. They're programming everything up in Python mostly. If it were me, it would be much more MATLAB and real-time Simulink, but hey, I'm a control guy, so I'm a little software shy. They're forced to dig into, even if you have a background in CS, you're forced to dig into enough physics that you can understand inverse kinematics, grasping, dropping of objects. You understand that gravity goes downward, and that's hard. It's the hardest thing about drones, isn't it, Tom Brady? They're doing localization and mapping, a very simple version of SLAM in this first course. The students have nicknamed it Robotics Boot Camp, okay? It takes them averaged about 35 to 40 hours a week for this course. Another course they're taking at the same time is by one of our favorite professors, who will go unnamed. Just kidding. It's me. So the students are being dragged through proof techniques. How do you do proof by contradiction, which sounds like a contradiction in terms? Enough linear algebra to be armed and dangerous. Then we take them through abstract inner product spaces, minimum distance problems, best approximation problems. They get the projection theorem and normal equations all worked out. They're doing recursive least squares, best linear unbiased estimation, minimum variance estimation. They're getting some practical stuff in matrices, singular value decompositions, QR factorizations, etc. Once they've done all of that, the Kalman filter is sort of like falling off a log. They've seen all of the recursive forms of the equations. And then we're not done there. We'll do enough real analysis that they understand open sets and closed sets from very fundamental principles, compactness, Cauchy sequences, fixed point theorems, etc. And then we end up with a user's tour of quadratic programs and linear programs. Now you would think with all of that, the course would have a terrible, terrible reputation. So the enrollment started out with 29 students the first year, because the room only would seat 30. Next year it doubled to 61, and the next year after that, the number of students tried to get in doubled once again, but the biggest room we could find is 100. So what it's doing is giving the students all the fundamental background they need to do mobile robotics correctly, machine learning, and all of the advanced stuff. We torture them the first semester, but after that, they're so well prepared for the rest of their courses in computer science, electrical engineering, mechanical engineering, aerospace, naval architecture, etc., that the program becomes super fun. So I hope you will come and be a part of this. And if you're in industry, you want our students. They are very, very, very well prepared. So once again, this is just a small subset of the faculty working with this. Let me give you a brief idea of some of the spectrum of research that we're doing. So I can't overemphasize this. I mean, almost every one of the faculty in robotics at Michigan touch hardware. It's not a theoretical exercise for us. We do the fundamental math, but then we also test it on machines. So by the time our algorithms get out in our papers, the stuff works, okay? You don't have to call us up and ask, what is the special sauce? It's all out there because we have gone through the implementation process. So autonomous vehicles, that's a given at Michigan. If you can't do that right at Michigan, then I don't know where else you could do it. But drones are super strong, as you saw earlier. But we have much more than that going on. I mean, there's a lot of really fundamental work in how people can interact effectively with robots, and whether that is through gestures, whether that is through language, whether that is through touch, etc. We have a very strong group in that. Locomotion of all kinds, whether it's flying, rolling, tracks, legs. Manipulation, I'll show you some really exciting things going on there. Cooperative robots that work in teams. We're building up strength in perception, because autonomy means you need to observe the environment and get information in. And then rehabilitation robotics is another big emphasis of ours. So here's just one example of our most recent hire, Dmitry Berenson, who started with us in January of this year. So you see the two humans on the right. They're able to reach around each other, plan for and make guesses about what the other human is going to do, and to work in a very cooperative manner. So what he is doing is trying to develop the algorithms so that robots can anticipate what you are doing, so that you can work side by side with them. And then you give them all of the hard stuff, and you get to have lunch, okay? While they just sit there and charge their batteries. So that's the idea. Yeah, we do need to work on another class on just treating robots with more respect and giving them a lunch break as well, but we haven't gotten that far yet. So when it comes down to doing something fundamental like manipulation is not the stuff that you see in a standard factory floor today. I mean, it's really mobile robots picking up objects in very complicated environments, or like this first video that was playing here. Dimitri's also working on objects that are very soft. So manipulating a solid object where you know what the shape is, etc., that's a fairly straightforward thing, but taking something like a sheet and spreading it out, it's a totally different problem, and in terms of mathematics, it's an infinite dimensional problem. One thing the new building will have, which is super exciting, is a 3-story fly lab. So once again, you will want to tour this building when it's open. It's going to be super exciting. So we're going to be very strong in the drone area. Another thing that's going to happen is, and this will open up probably sometime in the fall, is that there will be a very large, roughly 2-story tent put up next to the Space Research Building so that we can fly drones outside, in the wind, in the snow, in the rain, etc. And I think there's plans to do some robot racing like the week the tent opens. I wouldn't be surprised, okay? Turning once again to rehabilitation robotics, we have many, many researchers that are working on leg robots of one form or another. But one of the ways in which this work manifests itself into directly helping people, I don't mean the hypothetical thing of sending a robot into a complicated situation to rescue you from a collapsed building, which is another great way a leg robot can interact with people. But I mean, so you have suffered an injury to the body, whether it's neural or muscular or joint related. We are developing the devices that can be attached to your body that can help you recover this either through rehabilitation or permanent application of the orthotic or exoskeleton. If you happen to be so unfortunate as to lose an upper limb or lower limb, we also have some very, very fundamental work. And then Cynthia Chestek's lab has a very nice demo over here that you can see later on, but trying to take advantage of the existing neural connections in the body, the fact that you can still form images in your brain of what you want to accomplish and get that information connected to whether it's a hand or eventually legs. Henry covered very nicely our connection between robotics and M-City. I mean, the thing to remember about M-City, it's all hardware. There are no faculty really associated with M-City. So there's about 1/4 of the Robotics Institute that consists of faculty who are working on the area of autonomous vehicles, and they support what's going on at the Mobility Transformation Center, MTC, M-City, and the new center that Henry is launching. So part of that I'm very, very happy about is the open connected automated vehicles work, and there Wei Peng, who's the director of MTC, is teaming up with his managing director, Carrie Morton, and then a brilliant young faculty and faculty member at electrical engineering, Nejme Otsai, to get the car where it's set up to have a very ease of use case studies can be done. So what we want are people who are not experts in the entire ecosystem of autonomy to be able to work on their specific areas of expertise, and whether that is 3D processing, 3D point clouds, or in the case of Nejme on the right here, she's an expert in correct by construction control design. So this means developing software that meets a specification. And so you have a priori guarantees on the behavior of the closed loop system. And so she's working with Wei to make sure that her types of algorithms can be implemented easily in this car, and she is the first beta user. I'll take a last few minutes just to let you know about some of the exciting work that's been going on in my lab since my students have been here, and they've been very patient while I try to learn how to be a director. I was pretty much ignored them in the fall term, and they yet kept the lab going. So one of the things we've been trying to do is get robots that are outdoors as much as possible. We do work in the lab, but it's usually just to make sure that the hardware is working, tuning up a few things on the algorithm, then we do most of our testing outdoors. So this is the wave field, which is just outdoors of the aerospace building. It's got very challenging, undulating surface, and this robot is navigating it blindfolded. Okay, blindfolded. And you say, hey, blindfolded. Why would you make a robot walk blindfolded? Well, just get on YouTube and go GoPro fireman in your search, and you'll pull up all these videos of firemen who are in houses, and as soon as you get smoke and dust, all of your camera data just goes to pot. And so what you need to do is make sure your robots are fully robust and they can handle a lot of uncertainty in the visual data coming to it. So that's part of what we are working on. This is just last Saturday. We're out north of the mechanical engineering building. The university had done a controlled burn to get things ready for prairie grass, reduce fire hazards and stuff out there. The terrain looks pretty simple for a human when you've got your eyes open. You'll see in a little bit. It's even challenging for the humans as well. Whoops! Oh, human number one down. Let's see, we have one more human standing. Human still standing. Human has eyes closed in the back of his head. Human number two down. Okay, so the robot's doing just as well as the humans here, but the robot needs to do better. I'll skip this. Whoops, Shai Revson's work. I didn't want to cut that out. So we have other people doing legs in a totally different way. So these are robots that are modular. So imagine you could show up with a backpack and just assemble a robot on site to meet any particular demand that you have. So that's what Shai's group is trying to do. And so they make these things out of really inexpensive hardware and try to make algorithms that are super, super robust.